In this section, we're going to be looking at matrix solutions to linear systems. And in that section, we're going to be writing the augmented matrix for a linear system, performing matrix operations, and using matrices and the Gaussian elimination to solve systems. Right. We'll begin with the definition of what matrices are. And the singular form for matrices is a matrix. It is a rectangular array of numbers that are arranged in rows and columns. So what you see down here is a example of a matrix. It is in a rectangle, and we have rows and columns. Columns go up and down. Rows go straight across. And the numbers that are inside these brackets are called elements. So each individual number in this particular matrix are called elements. Okay, so if we want to mention the dimensions of this matrix, this is a 2-row, 6-column matrix. This has 2 rows and 6 columns. Okay, an augmented matrix has a vertical bar that separates the columns of the matrix into 2 groups. The coefficients of each variable are placed to the left of the vertical line, and the constants are placed to the right. And if any variable is missing, then that means that its coefficient is going to be 0. Okay, so what does an augmented matrix look like? Okay, let's say we had this. Now on the left side, we have a system of linear equations. In this case, we got 3x plus y plus 2z equals to 31. X plus y plus 2z is equal to 19. X plus 3y plus 2z is equal to 25. That's what we call a system of linear equations, because we have, in this case, 3 different equations in 3 variables, x, y, and z. This can be converted into an augmented matrix, which is what you see on the right. Okay, here we've got the vertical bar that separates the coefficients of x, y, and z from our constants. So for 3x plus y plus 2z is equal to 31, written in augmented matrix form, it would be just the coefficients. The coefficient of y is 1, the coefficient of z is 2. And our constant is behind this vertical bar, which represents the equal sign, by the way. In this case, 31 will be on the right-hand side. So in an augmented matrix, the first column is your x, the second column is the y, the third column is the z. And for x plus y plus 2z is equal to 19, the coefficients there for x will be 1, for y's coefficient is 1, for z the coefficient is 2, and then the constant is 19. And the same holds true for x plus 3y plus 2z is equal to 25. We write that as a 1, 3, 2, and then the constant 25. Okay, so that's how we write a system of linear equations in augmented matrix form. All right, now here's another example. This one we have x plus 2y minus 5z is equal to negative 19. Then y plus 3z is equal to 9, and then z is equal to 4. Here we got variables missing in the second and the third equation. Now the first equation, we do have an x, y, and a z. So we can write that in augmented matrix form as 1, 2, negative 5, and then negative 19 as the constant. But for the second one, we're missing an x term, so we need to put a 0 here. For y, the coefficient is 1. For z, the coefficient is 3. Then the constant is 9. And in the last equation, z is equal to 4. The x and the y terms are missing. So we put a 0 for the coefficient of x, a 0 for the coefficient of y. For z, its coefficient is 1, and the constant is 4. So as you can see here, if you have any missing coefficients, you have to compensate that with zeros there. Because the first column will be all your x's, the second column is your y's, the third column is the z, and then the numbers after the vertical bar represent the constants. Okay, let's look at this example here. Let's say we want to determine if the ordered triple, and by the way, an ordered triple has three numbers, an x, y, and a z. In this case, the ordered triple is 10, -7, 11. We want to determine if that ordered triple is a solution to this system. X plus y plus z is equal to 14. X minus 2y minus z is equal to 13. 2y, 2x minus y minus z is equal to 5. We want to determine if this, with this ordered triple, satisfies this system. Okay, let's look at this. We have to replace the x, the y, and the z in each one of these linear equations. So when I move this out the way, let's start with the first equation. X plus y plus z equals 14. Okay, now we're going to replace the x with 10. The y, we're going to replace that with -7 because that's what the ordered triple for y is, and then z is 11. That should equal to 14. In this case, our ordered triple that we're dealing with is 10, -7, and 11. That's our ordered triple. Now, when we simplify this, 10 plus -7 is 3, plus 11, it should give us 14. And if you add 3 and 11 together, you do get 14. So we know that this ordered triple satisfies this first equation, but it must satisfy all three equations. So we go to the next equation, which is 2x. Take that back. X minus 2y minus z is equal to 13. X minus 2y minus z equals to 13. So in this case here, we replace the x with 10, the y with -7, and the z with 11. So here, we can have 10 minus 2 times y, which is -7, minus z, which is 11. That should equal to 13. The left side should equal to the right side. So in this case here, let's simplify this. Bring down to 10. Minus 2 times -7 will be plus 14. Minus 11, that should equal to 13. Then 10 plus 14, that's going to give us 24 minus 11. That should get equal to 13. And 24 minus 11 does equal to 13. The left side does equal to the right side. So we can say that this ordered triple satisfies the second equation. So far, the ordered triple satisfies two of them, but it must satisfy the third one as well. Okay, so now that third equation was 2x minus y minus 2z is equal to 5. And we replace the x with 10, so it'll be 2 times x, which is 10, minus y, which is -7, minus 2 times z, which is 11. That should equal to 5. In this case, 2 times 10, that's 20. Minus the -7 would just be plus 7. Minus 2 times 11, which will be 22. That should equal to 5. So here, 20 plus 7 is 27, minus 22. That should equal to 5. And if you subtract 22 from 27, it does equal to 5. So here, that ordered triple, 10, -7, and 11, satisfies that third equation. In fact, it satisfies all three equations. So here we can conclude that the ordered triple, 10, -7, and 11, is the solution to this system of linear equations. Okay. All right. Okay, let's look at an example here. Let's say we want to write the augmented matrix for this system of linear equations. And here we got the linear equation 9x plus y plus 7 is equal to 4, 3x minus 8y minus z is equal to negative 7, x minus 2y minus 2z is equal to negative 5. And here we want to write an augmented matrix for this system of linear equations. So I'm going to erase this here. And we're going to write down that equation, those order triple, that system of linear equations that we have here. 9x plus y plus 7z equals 4. Then 3x minus 8y minus z is equal to negative 7. And then x minus 2y minus 2z is equal to negative 5. Okay. So this is what my matrix is going to look like. Okay. Now that first equation, 9x plus y plus 7z is equal to 4, I'm going to write just the coefficients. The first column is the x, the second column is the y, the third column is the z, the vertical bar represents the equal sign, and the final column after it represents the constants. So I'll write this as a 9, because that's the coefficient of x. The coefficient of y is 1, and the coefficient of z is 7. And my constant is 4. So I have a 9, a 1, a 7, and a 4. And then the second equation, 3x minus 8y minus z is equal to negative 7. Those numbers are written the same way. 3, then negative 8, and then negative 1, then negative 7. And for x minus 2y minus 2z is equal to negative 5, it's going to be written as a 1, then negative 2, negative 2, negative 5. And that's all there is to it. That's how we write a system of linear equations in the form of an augmented matrix. Okay. Now another example would be this. Let's say we want to write an augmented matrix for this system. Here we get x minus y plus 8z is equal to 5, y minus 12z is equal to negative 11, then z is equal to 4. Okay, so we want to write this as an augmented matrix. So here's what we have. X minus y plus 8z is equal to 5. And then y minus 12z is equal to negative 11. And then the last equation, z is equal to 4. Okay, that's my system of linear equations. And I want to write that as an augmented matrix. And here's what we do. Just write down, do our brackets, then our vertical bar will separate our coefficients of the variables x, y, and z from our constants. The first one, x minus y plus 8z is equal to negative 5. We can write that as 1, negative 1, 8, and 5. That first one was quite easy. Now for the second one, you got y minus 12z is equal to negative 11. Notice that we're missing an x term. So its coefficient for the x is going to be 0 here. But for y, the coefficient is 1. And for z, the coefficient is negative 12. Then that's equal to negative 11. Now for z is equal to 4, the x and the y terms are missing, so we need to put a 0 here and a 0 here for the x and the y. For the z, the coefficient is 1, and our constant is 4. So that's how we write this as an augmented matrix. Okay. Okay, now let's look at this. Let's say we were given an augmented matrix and we want to write this as a system of linear equations that is represented by this augmented matrix, which is in this case 4, 0, 3, negative 17, 0, 1, negative 6, 14, 9, 7, 0, 2. Okay, and I'll rewrite this. In this case here, this is our augmented matrix that we have, which is 4, 0, 3, negative 17, then 0, 1, negative 6, 14, 9, 7, 0, and 2. And here we want to write this as as a system of linear equations. Now keep in mind the first column is your x, the second column is the y, the third column is your z, and then the last column is your constants. So this first row, 4, 0, 3, negative 17, that 4 represents your coefficient of x, that's going to be 4x. 0 is the coefficient of y, so we don't have to write down plus 0 y. But for 3, that coefficient is z, so it'll be 4x then plus 3z, and that's equal to, represented by this vertical bar, then negative 17. Okay. So that's the first linear equation. The second one, 0, 1, negative 6, 14, the coefficient of x is 0, so we don't need to write down 0x. But for the 1, the coefficient for that is y, so that will be just y. Negative 6 is your coefficient for z, so we can say minus 6z. That's equal to 14. And then for 9702, the coefficient for 9 is x, so that'll be 9x. The coefficient for y is 7, so it'll be plus 7y. The coefficient for z is 0, so we don't need to write down 0z. But so 9x plus 7y will be equal to 2. So this represents the system of linear equations here. 4x plus 3z is equal to negative 17. Y minus 6z is equal to 14. And 9x plus 7y is equal to 2. Okay? So that's how we write a system of linear equations that's represented by an augmented matrix. Okay. Now let's talk a little bit more about augmented matrix here, because we're going to look at how to solve an augmented matrix. Our goal in solving a system of linear equations in 3 variables using augmented matrices is to produce a matrix with ones down the diagonal from the upper left to the lower right on the left side of the vertical bar, which is called your main diagonal, and zeros below the ones. So we're going to create a matrix in a way that we only have ones along the main diagonal, and that's from upper left to lower right on the left side of the vertical bar, and zeros will be underneath those ones. And here's an illustration of just that. Because what we want is just ones along the main diagonal. This is the main diagonal right here. And then you're going to have zeros underneath it. Okay? And in this case here, A, B, C, D, E, and F, those are real numbers. And when we write it in this way, where we have ones along the main diagonal and zeros below the ones, the third row gives us a value in one variable, usually the z value, because x is your first column is your x's, the second column is the coefficients of y's, the third column is the coefficient of z. And usually in the third row, z will be equal to some numerical value. for y and x and y, we can find out what those are by using what they call back substitution. Okay, because we'll substitute z in for the value in for z in the second equation to find out what y is. Once we find out what y is, we'll take the values of y and z, put those in for the y and the z in the first equation to find out what x is. Okay, this is what we call back substitution. Okay, a matrix with ones down the main diagonal and zeros below the ones is said to be in this particular form, which is called row echelon form. Row echelon form is where you have ones along the main diagonals and zeros below those ones. And we use row operations on the augmented matrix. So the next thing we're going to look at is row operations. The following row operations produce matrices that represent systems with the same solution set. And these are your matrix row operations here. Two rows of the matrix may be interchanged. That means you can swap any two rows in order to get like the ones in the position that you need for them to be at. Number two, the elements of any row may be multiplied by a non-zero number. And then third, the elements in any row may be multiplied by a non-zero number, and these products may be added to the corresponding elements in any row. And also, two matrices are row equivalent if one can be obtained from the other by a sequence of row operations. So in other words, this is just in shorter terms here, in shorter sentences. Each matrix row operation can be expressed symbolically as follows. We can interchange the elements in the ith row and the jth row. That means row I can be interchanged with row j. And then number two, you multiply each element in the ith row by some constant called k. So it'll be k times row I. And then number three, you can add some constant times the elements of the row I in row I to the corresponding elements in row j. So you can do k times row I plus row j. And k could be a constant, positive, or negative. Okay. Now let's look at let's look at this example here. Here we want to use the matrix below and perform each indicated row operation. All right, in this case here, we got this particular matrix, and we want to perform these three indicated row operations here. Now what I'm going to do here is rewrite this so that you can see this a little bit better. Now the row that we're looking at, the matrix that we're looking at is this. You've got 4, 12, negative 20, and then 8, which is on the right side of the vertical bar. Then the next row is 1, 6, negative 3, 7, and then negative 3, negative 2, 1, and 9. Okay, that's your matrix here. And the first one we want to do here is use this matrix to find, in part A, we want to interchange row 1 with row 2. That's what this symbol means. Interchange row 1 and row 2. Okay, here's row 1 and row 2. We're just going to swap these two rows. Okay, so that means this matrix, when we interchange row 1 and row 2 becomes row 1 becomes row 2. So 1, 6, negative 3, 7 goes in row 1, whereas 4, 12, negative 20, and 8 goes in row 2. And then row number 3, we'll just go ahead and rewrite that because that's not going to change. Okay, this is what your matrix will look like after interchanging row 1 and row 2. Okay. All right, now look at part B. We want to take 1/4 of row 1. Okay, so this is our matrix that we're looking at here. Now go ahead and rewrite that again. But here we want to take 1/4 of the first row. 1/4 of row 1 is going to be dealt with. So row 1, we want to take 1/4 of this, or divide by 4. Divide each element by 4. And when we do that, we take 1/4 of 4, or 4 divided by 4, which will be 1. 1/4 of 12, or 12 divided by 4, will be 3. 1/4 of negative 20, or negative 20 divided by 4, would be negative 5. And then 1/4 of 8, or 8 divided by 4, would be 2. Okay, so that new row 1 will be 1, 3, negative 5, and 2. The other rows will remain the same. So I'll go ahead and bring over 1, 6, negative 3, 7, and then negative 3, negative 2, 1, and 9. Okay, so that's what this matrix will look like after you've done 1/4 of row number 1. Okay, and then part C. Now let's look at this one. We got 3 times row number 2, and we're going to add to it row number 3. In this case, row number 3 is going to change. Okay, so let me rewrite this, the original matrix that we started off with. Now we're going to do 3 times row number 2 and add to it row number 3. We'll come up with a new matrix here. All right, in this case here, the first 2 rows will remain the same. So I'll go ahead and bring over the 4, the 12, negative 20, and 8. And then the second row remains the same. But here's how we're going to come up with this new row number 3. We're going to take 3 times each element in row number 2 and add it to the corresponding element in row number 3. In other words, we got 3 times 3 times 1. That's going to give us 3. Add that 3 to this negative 3, and you're going to get 0. So that 0 goes there. And then 3 times the 6. That's 18. 18 plus this negative 2 is 16. And then 3 times this negative 3 is negative 9. Negative 9 plus 1 is negative 8. And then finally, 3 times the 7 here, that's 21. 21 plus 9 is 30. Okay? So this is what you will get after you've done 3 times the second row plus row number 3. Okay, and let me double check here because I think I made a mistake right here. This should be negative. Okay, this should be negative 9 here. Okay, and I need to go back and do this one. This 3 times, that's 21. 21 plus a negative 9, this should be 12. So instead of 30, this should be 12. This goes to show you what happens when you leave off your signs here, okay? Because the original problem had negative 9 in it. Negative 3, negative 2, 1, negative 9. And I think the others, pretty much in part A and part B, they pretty much remain the same. So, okay. Okay. But that's how you would do the matrix row operations here. Okay. And do pay close attention to your signs, because if you leave those signs off, you can easily get wrong answers there. Okay. All right, next we'll look at solving a linear system using what they call the Gaussian elimination, and it's named after a mathematician who invented this type of method of solving a system of linear equations. And this is where we use the matrix row operations here. Okay, you first write the augmented matrix for the system. It'll be given to you as a system of linear equations. You just need to write it as an augmented matrix. Then you use your matrix row operations to simplify the matrix to a row equivalent matrix in row echelon form, which is where you have ones down the main diagonal from the upper left to the lower right and zeros below the ones, which is what we just got through talking about here, because this is the end result that you want. Ones down the main diagonal and zeros that are underneath it. And then this is where you'll use back substitution to find the solution to that system of linear equations. Okay. Now we're going to do one that has where we're going to do the matrix row operations here, like this one. We're going to use matrices to solve this system. Okay, so in this case here, we have 2x plus y plus 2z is equal to 18. And then we got x minus y plus 2z is equal to 9. And then we got x plus 2y minus z is equal to 6. And this is the system that we're going to use to solve using matrices. Okay, now the first thing I'm going to do here is convert this into an augmented matrix. All right, and if you remember how we convert that to an augmented matrix, we take the coefficients of x, y, and z. They go on the left side. The constants go on the right side. So for the x's, it'll be a 2, a 1, and a 1. Okay. And then for the y's, it'll be 1, negative 1, and 2. And then for the z's, it'll be 2, 2, and negative 1. Your constants are 18, 9, and 6. Okay, so that's your augmented matrix. Now we're going to use our row operations to solve this system of equations here using matrices. Okay, now my first objective is get ones along the main diagonal here. I'm going to use this second row right here, and I'm going to interchange the first row and the second row because I want a 1 up here. So what I'm going to do here is say interchange row 2 with row 1. Okay. Row 2 will be interchanged with row 1. So what I'm going to do here, here's my new matrix. This row 2 becomes row 1, so I'm going to write 1, negative 1, 2, and 9. Then row 1 becomes this row 2 right here would be 2, 1, 2, 18. The third row is going to remain the same, so it'll be 1, 2, negative 1, and 6. Now, here's what I want to do here. Now that I have a 1 here, I need to put zeros here underneath it. This is where I'm going to put a 0 here. I have a 2 right here. For this to be a 0, I need to do negative 2 times row number 1. Because I'm going to take negative 2 times row 1. Here these signs are the same, so I need to make one positive and the other one negative. So I need negative 2 times row 1. Then I'm going to add that to row number 2. Okay? And I'm going to do this also. To save time and space, I'm also going to want to make this a 0 right here underneath that as well. So let's do this. The opposite of row 1 plus row 3. So I'm doing 2 matrix row operations in one step. Okay, so now here's what I'm going to have for this next matrix here. The first row remains the same, so I'll bring over the 1, negative 1, 2, 9. But for the second row, it's going to change. Negative 2 times row 1. Each element in row 1 will be multiplied by negative 2, and then it'll be added to row 2. So negative 2 times this 1 is negative 2. Negative 2 plus 2 is 0. And then I'm going to do the same for the rest. Negative 2 times this negative 1, that's a positive 2. Positive 2 plus 1 is 3. 2 times that negative 2 is negative 4. Negative 4 plus that 2 is negative 2. And then negative 2 times 9, that's negative 18. Negative 18 plus 18 is 0. Okay? Now for the third row, I'm going to take the opposite of row 1 plus row 3. So here, the opposite of 1 is negative 1. Negative 1 plus 1 is 0. Then the opposite of negative 1 is 1. 1 plus 2 is 3. The opposite of 2 is negative 2. Negative 2 plus negative 1 is negative 3. The opposite of 9 is negative 9. Negative 9 plus 6 is negative 3. Okay? Now, it seems like I might not be able to get anywhere with this, but look at this last row. I got 3, negative 3, negative 3. I can take 1/3 of that row. 1/3 of row number 3. Okay? So I'm going to need to start this on a new line here. Now keep in mind these first 2 rows are going to remain the same. So I'm going to have 1, negative 1, 2, and 9. And then 0, 3, negative 2, and 0. But when I take 1/3 of this row, 1/3 of 0 is 0. 1/3 of 3 is 1. 1/3 of negative 3 is negative 1. And this will be negative 1 as well. 1/3 of negative 3. Now, why don't I interchange row 2 and row 3? Because I want a 1 in the middle diagonal. This main diagonal has to have a 1. This has to have a 1. That must have a 1 as well. So it'll be easier to interchange row 2 and row 3. So row 2 will be interchanged with row 3. So row 1 remains the same. but row 2 becomes row 3, and row 3 becomes row 2. So row 3 will have 0, row 2 will have whatever row 3 was, 0, 1, -1, and -1. And then row 2 becomes row 3, 0, 3, -2, 0. Okay, so I got a 1 in this, I got 2 1s in this main diagonal here. Now, what I'm going to do here is get a 0 underneath this one right here. I got a 3 here, so I need to do -3 times row 2 plus row 3. Now, I'm not going to do -3 times row 1 because if I did that, I'm going to have a 1 here. Actually, I have a -3 here, which I don't want. It'll be easier to work with row number 2. Take -3 times row 2, and then add that to row 3. And here's what I'm going to come up with. The first 2 rows remain the same. And in this case here, -3 times row 2 plus row 3. So -3 times 0 is 0, plus 0 is, of course, 0. -3 times this 1 is -3. -3 plus 3 is 0. -3 times -1 is 3. 3 plus -2 is 1. And then -3 times 1 is 3. 3 plus 0 is 3. Guess what? I'm done. Because now I have 1s along the main diagonal and 0s underneath those 1s. So here, this particular matrix is now in row echelon form. Okay? Now, let's convert this back into a system of linear equations. So you'll see what this is. That 1, -2, 1, -1, 2, and 9 means this. That first equation is x minus y plus 2z is equal to 9. That's from this first equation here. Now here's the second equation. Y minus z equals to 1. And then the final one is z is equal to 3. Okay, see, z is equal to some numerical value. In this case, is 3. Now, this is where I use back substitution to come up with the value of y and the value of x. Since z is equal to 3, let's substitute 3 in for this z in the second equation. So here we're going to have y minus, now z is equal to 3, equal to 1. Y minus 3 is equal to 1. Now solve for y by adding 3, you're going to get y is equal to 4. Since y is equal to 4, z is equal to 3, let's substitute those values into the first equation to find out what x is. So now you get x minus y, which is 4, plus 2 times z, which is 3, that's equal to 9. Let's simplify this. X minus 4 plus 2 times 3 is 6 is equal to 9. And then minus 4 plus 6 will give you plus 2. So x plus 2 is equal to 9. Wait a minute. I think I made a mistake right here because, oh, I see where. This should be -1, which means y minus z is equal to -1. And instead of y being equal to 4, when you add 3, y would be equal to 2. Okay? So instead of y being equal to 2, this will be x minus 2. Okay? And then minus 2 plus 6 would be 4. So it'd be x plus 4 is equal to 9. Okay, so it's important that you not leave off your signs, otherwise you can get wrong answers here, like I did before. Let's see, if you subtract 4, now x is equal to 5. Okay, so now x is equal to 5, y is equal to 2, z is equal to 3. That's my order triple. And you can always go back and substitute this order triple in the original equation to see if that order triple satisfies each one of those. And if I was wrong, then I made a mistake somewhere. And I was able to catch this mistake right here by leaving off that -1 here. Okay, so that's how you solve a system of linear equations using an augmented matrix and using matrix row operations.